Okay, welcome to the continued 3DEC training. This is a relatively short section about initial conditions and boundary conditions. And again, this is Jim Hazard speaking, 3DEC product manager here at ITASCA. Okay, so initial conditions. In geomechanics, we almost always have some sort of initial conditions that exist in the soil or rock, basically due to gravity. This is different from modeling you might do in, say, mechanical engineering, where you're modeling machine parts or something like that, and they're initially under zero stress. In the geomechanics world, almost always we're starting at some stress state in the material that we're trying to model. These can be stresses, or they can be pore pressures, or they can be both. We have to decide if we want to have changing stresses with depth, which is, of course, what happens in reality, but that may or may not be important. If you're very deep underground, the change in stress from the top of the model to the bottom of your model due to gravity is negligible compared to the stress in the model deep underground. So in these deep underground simulations, maybe you don't need to vary the stress with depth. If you're close to the surface, almost certainly you do want to vary the stress with depth and turn on gravity. The advantage of specifying these initial conditions is that it allows the simulation to come to equilibrium quite quickly. It is certainly possible to set up a model without initial conditions, as we have done in previous examples, and then you can turn on gravity and let it come to equilibrium. But if you set the initial stresses to balance that gravity, you will get to initial equilibrium much more quickly. So almost always the way to do that in 3DEC, at least in a situation where the initial stresses change with depth, is you use this block in situ command. So you say block in situ topo or topography, and this will automatically work out the stress in each zone based on the weight of material above that zone. So we will look at the densities and the sizes of all of the zones above any given zone and calculate the vertical stress just due to gravity and weight of material. So it calculates the vertical stress, and then you specify a ratio of horizontal to vertical. And you can have a different ratio in the X direction and the Y direction. It is also possible to specify an overburden stress on top. So in this example shown here, the surface of the model is the actual surface of the Earth. So there's likely zero stress acting on the surface. But you can imagine you want to model something that's quite deep, and you don't necessarily want to model all of the material between your excavation and the surface. So you can truncate that at some point and add an overburden stress to account for the material that you're actually not modeling. And just be careful here because, again, compressive stresses are negative. So if you specify an overburden stress, you almost certainly want to give a negative number. Note that this command applies stresses to both the zones and the joints. We haven't talked about joints yet, but in general, you want to have stresses in the joints and the zones due to gravity when you specify the in situ stress, and this command will set them both. So you can see how this works on the right-hand plot. This is a model with some sort of mountainous topography. There's a joint set in here. The colors indicate the vertical stress. So obviously there's higher stress at the bottom than at the top. Again, the compressive stresses are negative, so they're most negative at the bottom. But we've colored the contours to show red as being highly compressive. In the joints, these are colored from light to dark, with light being low normal stress and dark being high normal stress. And again, higher normal stresses down deep. And what's interesting here is there's a little blob of low density material, just to show you how the algorithm works. So you can see that below this blob of low density material, we see lower stresses than we do to either side where there's higher density material. So the algorithm works pretty well. Of course, the stresses will not be perfectly balanced unless the top surface is perfectly horizontal. So you will still need to run some number of cycles after specifying the initial stress. And as I said before, sometimes you might be very, very deep and you don't necessarily care about the change in stress with depth. In this case, you can just specify a constant stress, and the command might look like this: block in situ stress, and you give 6 components, or commonly, at least in mining, block in situ principal, and you give principal stress magnitudes and principal stress directions. And again, in both cases, be careful that compression is negative. Okay, that's all I'm going to say about initial conditions. Boundary conditions. We need to have boundary conditions because we are not modeling the entire Earth. If you are modeling the entire Earth, obviously you would not need to put in artificial boundaries. But we do need to put in artificial boundaries because we have to truncate the model somewhere. And so the trick here is to decide A, where to put the boundaries, and B, what kind of boundaries we want. So where to put the boundaries? We do not want the boundaries to be too close to the area of interest. If you have failure around a tunnel or an excavation that extends out to the boundaries are probably too close. If you have significant displacement extending out to the boundaries are probably too close. In a model with failure in it, in 3D, there's kind of a rule of thumb that you want to put the boundaries at least 2 times the radii of the equivalent spherical volume of the excavation. If there's not much failure, you probably want the boundaries to be even further away than that. Okay, so what type of boundaries do you want? By default, if you don't do anything, the boundaries are free. So for the surface of the Earth, or the surface of your model, if it corresponds to the surface of the Earth, you do not need to specify anything, and it's just a free surface. The other boundaries, you need to do something, and your choices are essentially displacement boundary or a stress boundary. Both of these will be incorrect in different ways. The displacement boundary will underestimate displacement and overestimate stress, and a stress boundary will overestimate stress and underestimate displacement. So to some extent, it doesn't really matter which one you choose. They're both going to be wrong. You can overcome that, of course, by putting your boundaries further away from the area of interest. And it's kind of a judgment call to decide which way to go with these boundaries. However, you should probably not assign stress boundaries to all of the boundaries, because then you don't have anything fixed, and it's possible for the entire model to start rotating. And I've seen this happen, and it is certainly possible. If things aren't perfectly balanced and you have all these stress boundaries, then the whole model might rotate. So probably you want to have at least one of your boundaries fixed, displacement boundary condition. Okay, I mean, that's pretty much all I'm going to say in terms of PowerPoint. This will all become a little bit clearer if we look at an example. And I've given you this example with the material that you hopefully downloaded. And so we're just going to load it up and look at it. So I will start 3DEC. Okay, this time I will open an existing project. We don't necessarily need to type everything in here. We can just look at one that's already exists. So I open existing project, and you want to navigate to where you downloaded the material. All right, so there's a directory number 4, running models. Inside of that is a directory called tunnel, and you can open up that project, tunnel.prj. So this is already set up for you. There are 3 different data files you can see. There are 3 different plots. And by the time they're done, there will be 3 different save states as well. You can see the lines through them here means that we haven't actually solved them yet. So there's a few new things in this example. Let's make this font a little bit bigger. So model new you've seen before. Model large strain off you've seen before. This is a new command, model create tunnel. And this is a command that is used to easily create a circular tunnel. It's not necessarily used that much in reality because generally your tunnels aren't circular. But for doing simple examples like this, it's a relatively quick and easy way to just create a circular tunnel. And what it does is it creates a whole bunch of blocks at a given center. The length of the tunnel, generally in the y direction from, say, -1 to 1, the radius of the tunnel, the distance to the boundary, this is the number of diameters or radii, I think, to the boundary. Radius ratio, so the blocks actually get bigger as you move towards the boundary. The number of blocks in the radial direction, the number of blocks in the tangential direction, the number of blocks in the axial direction. If you want to dig into the details of what all these commands are, again, put your cursor at the end of block create tunnel and hit F1, and it tells you everything you need to know here. So for example, it's useful to look at this because blocks tangential is not the number of tangential blocks around the whole tunnel, it's the number of tangential blocks in one 45-degree segment. So the number of tangential blocks around the whole tunnel is actually 8 times that. So in our case, we're going to have 40 blocks around the tunnel. Almost always after you've created the tunnel, you will join these together. These are not real joints. We do not want to set cohesion and friction and have them sliding and failing. It's just a way to create the tunnel by sticking together a whole bunch of blocks. So we can run the first 10 lines here. And this is a useful trick that I haven't shown you yet, but you can select the lines that you want to run and right-click and choose Run Selection. And instead of running the whole file, it will just run the lines that you selected. So it actually creates 420 blocks and joins them together. We can go over to the plot called blocks and have a look at it. So this is actually contouring by displacement magnitude, which is 0, because we haven't run anything yet, but you can see the blocks. And we've got all these blocks that define the circular tunnel, and they're all joined together. The join means that there will not be any force or displacement calculation at these joints, so that they essentially behave as if there's no joint there at all. This allows you to use the block logic to create geometries, but not necessarily calculate the problem as if they were real joints. Okay, if we go back to the data file, now we are doing some zoning. So in the previous example, you saw block zone generate edge length, and you just gave an edge length for I can't remember what number we used, 1, and it's filled up the volume with tetrahedra, and they'll have the same edge length. Sometimes you might want to have a gradation in zone size, especially in a case like this where you have a tunnel, which is a region of interest, and you want to grade the zone size out from that. So there's some new zone generation logic in version 7 and version 9. The command for that is block zone gen new, which is a little bit different than what we saw before, which was block zone gen. If you're interested, what this does is it actually uses the griddle zoning logic. It's the same libraries that griddle uses to generate zones or blocks. It's built into 3DEC. So we can use that here because we want to have a gradation of zones from the middle to the outside. This new griddle-based zoning logic gives you more flexibility when it comes to gradations and things like that. So, so you can give it, first of all, you have to specify the size of the zones that you want to generate, and then you have to generate them. So the first command, block zone size, you give the center location, At a distance 1 of 1.5 meters, the edge length will be 0.2, and at a distance 2 of 6 meters, the edge length will be 0.8. So we got a gradation of edge sizes from 0.2 to 0.8 between 1.5 and 6. And everything less than 1.5 will just get the same minimum zone size here. So we've defined all the sizes, and then we just generate the zones. Block zone, generate new, minimum edge length 0.2, maximum edge length 0.8. So we can just run these two lines. So it thinks about it for a few minutes. Doing some zoning, there you go, generating mesh. Zoning, zoning, zoning. There we go. We can go back and look at the block plot. Now we can see that these blocks have been zoned. It's not totally clear which boundaries here belong to the blocks and which belong to the zones. You can actually turn off the zone boundaries if you want. So if I click in the plot item list under block displacement magnitude, there's a checkbox here for zone faces. I can uncheck that. So there's the original blocks. And here's the blocks with the zones. And you can see how there's smaller zones in the middle and bigger zones towards the edges, which is what we wanted. Okay. For this example, we will assume that the material is elastic. So block zone C model assign elastic. And when it's elastic, we only need to give three properties: the density, the Young's modulus, and the Poisson's ratio. We will record a vertical displacement at the top of the tunnel. We've seen this before. We'll record the minimum stress at the side of the tunnel. Remember, compression is negative. So when I say stress min, I actually mean the maximum compressive stress. And I've even left myself a comment here to make it clear. Here are the initial conditions that I talked about. In this case, we're assuming it's a deep tunnel. We're not going to have a variation in stress with depth. We're just going to have a constant. So block in situ stress, this is the XX component, so 0.5 megapascal compression. The YY component, 0.5 megapascal compression. The ZZ component, 1 megapascal compression, and all the shear components are 0. So this sets up the initial stress, and it saves it. We have not set up the boundary conditions yet, because what we're going to do is explore the two different types of boundary conditions in these two other files. But we can run this whole thing. So you can run the whole file, obviously, by pressing this green arrow. And we'll go through and do everything, and give you some information down here as it goes. And then it saves it. You'll see here, I actually have mine set up so that it automatically compresses the save files. By default, it doesn't do that, but if you want to save on hard drive space, you can set that up. If you go to Tools, Options, under General, there's a checkbox that says Compress New Save Files and Result Files. You can check that, and it will automatically compress them. The advantage, of course, is that it uses less hard drive space. The disadvantage is that it takes a little bit longer to do the saving and restoring. You will see here under the save states that there's a little green line next to the name. It indicates that it's compressed. Okay, so we set all that up. We can go and look at the blocks again. The displacement is still 0. We haven't done anything. But we can look at the stresses. So under here, under the attributes, we're still looking at contours, but we can change the value to stress. So by default, it's showing me the XX stress, and it's constant everywhere, minus 5E5. I could change it to the ZZ stress, still constant everywhere, but now it's minus 1E6. Okay, let's change this back to displacement. And let's look at what happens when we use displacement boundary conditions. Note that the boundary is quite close to the tunnel here. And And we're running this thing elastically. So the boundary is going to have some effect on the results for sure. If there was a fair amount of failure around this tunnel, that would suck up a lot of stress and maybe the boundaries wouldn't have that much effect. In this particular case, you will see that the boundaries are probably too close to the tunnel. So let's look at this file, bc-disp. We're going to take this model, we're applying boundary conditions, displacement boundary conditions. And again, because this is an explicit program, we don't actually specify displacements, we specify velocities. Everything is in terms of velocities. But obviously, if the velocity is 0, the displacement will also be 0. So we can specify all 3 components of velocity to be fixed on the left side at x equals -7.5. We can specify all 3 components of velocity to be fixed on the right hand, x is 7.5. Now, how do we figure out these coordinates? Remember, we built this model and we said, block create tunnel, boundary 4, so I put the boundary out at some distance away from the middle, and I don't necessarily know what that is. If I'm not sure where those boundaries are, I can go to my plot, I can spin it a little bit here, and just hover my mouse over the left-hand side, and the information box there on the bottom right will tell me the coordinates where my cursor is. So my cursor is hitting -7.5, 0, point something, 1 point something. So this left-hand side is at x -7.5. The right-hand side is at x positive 7.5. Right? Now, if I get spinned around like this, and I want to get back to the original state, remember I can just hit this little square with a button in it that resets the view. Okay, so back to bc-disp.dat. I'm fixing all components of velocity on the left side, all components of velocity on the right side. If I jump down a couple lines, I'm fixing all components of the z velocity, sorry, all components of velocity on the top and all components of velocity on the bottom. On the front and the back, I'm only fixing the y component. And again, we're assuming this is symmetric out of the plane. So really, this is a 2-dimensional model, a plane strain type of model. Obviously, 3DEC is a 3D code, so it's got some thickness to it, but we can make it behave like a plane strain model by just fixing the y velocity on the front and the y velocity on the back. And this basically makes it behave as if there was an infinitely long tunnel. All right, we can solve that. Probably nothing will really happen here. We've installed in situ stresses, we've fixed the boundaries, but we haven't excavated anything. So if we solve that, it'll probably only take a couple of cycles to reach equilibrium. It gets interesting here. So on line 21, we're essentially excavating the tunnel all in one shot. In reality, you probably wouldn't do that. You'd probably do this more gradually. In this case, the model is elastic, so it really doesn't matter. Even if there's a big shock to the system that occurs by excavating this thing all in one step, it kind of doesn't matter. You know, there'll be some waves bouncing around. It will come to equilibrium. Nothing fails because it's elastic. You'll get the right answer in the end. So we can do this in one shot. Block delete, and then we give a range to define the tunnel. Remember, we set up the tunnel has a radius of 1.5, so we just define a cylinder with a radius slightly bigger than that to encompass the tunnel and all the blocks that make up the tunnel. We give the starting N1 coordinate, N2 coordinate, and the radius, and it will delete all of the blocks inside of that cylinder. Then we solve. We know it will solve because it's elastic, and then we save it. So we can run this whole thing. There we go. We solved it. It took the first solve command after we applied the boundary conditions required 2 steps. So like I said, everything was balanced. I'd only needed 2 steps. And then it did another 1007 steps to solve after we deleted the tunnel. We can go look at the block plot. So now we're looking at displacements. Remember that the vertical stress was twice as high as the horizontal stress. So we're getting more displacement at the top and the bottom than we are at the sides. Displacement here is about 20 centimeters or so. I guess this is pretty soft material. See, these blue squares are showing you the history locations. So we can go and look at the histories. So history of displacement at the top. There's a big negative, and then there's a bit of a bounce, and then it comes to equilibrium. So again, around about 20 centimeters of displacement. We can look at the stress. This is the the maximum compressive stress on the side of the tunnel. Again, a big increase in compression, a bit of a bounce, and it comes to equilibrium at around about 2 MPa compression. If you want, so this is a plot showing the displacements. We could also show stress. So if we change the contour from displacement to stress, again, by default, it's showing the ZZ stress. Maybe we want to look at the minimum principal. And again, remember, because compressive is negative, minimum principal is actually the maximum compression. So we hit minimum principal. So we see the highest compressive, remember the maximum stress is vertical. So what you'll see is highest stresses around the edges here. The maximum compressive stress is around the edges. It's a little bit disconcerting to see this plotted as compression negative. So there's actually a checkbox in the plot attributes. So if you clicked on block minimum principal stress in the plot item list, you look in the attributes, there's a checkbox that says comp plus. And what that will do is flip the plot around so that compression is positive. This is more intuitive for those of us in the rock mechanics world. So now we're seeing high compressive stresses around the edges and less stresses at the top and the bottom. You will notice that what it does is it gives every zone its own color. These are tetrahedral zones, constant strain tets. So every tet has a single stress associated with it. However, it makes for kind of a not that beautiful plot. So you can smooth that out a little bit. If you go over here to the attributes, and it says method constant, what that means is every zone has its own constant stress. But I can do a little bit of smoothing here. If I choose the first drop-down option, volumetric averaging, it actually smooths the stresses out over the zones, and so I can see something that looks a little bit nicer. Okay, so that's the situation with displacement boundary conditions. If we change the contour back to displacement, you can see, well, it's blue everywhere, but if you hang your mouse over the edges here and look in the information box, you'll see that the value is 0. So the displacement of the grid points on the sides is 0 because that's what we told it to do. If we move our mouse closer to the tunnel, you will see the value increasing. We're getting more displacement. Now, let's see what happens with stress boundary conditions. So we go to the data file bc-stress, storing the same starting state. But this time, instead of fixing the boundaries, we're applying stresses. Block face applies stress XX, and this is set up to balance the in situ stress. So remember, the in situ stress was 0.5 megapascal in the horizontal direction and 1 megapascal in the vertical direction. So here we're applying 0.5 megapascal of compressive stress to the left side, 0.5 megapascal of compressive stress to the right side, 1 megapascal of compressive stress to the bottom, 1 megapascal of compressive stress to the top. And we're still assuming that this is basically a plane strain problem, so we're fixing the wide position on the front and the back. Notice when we're applying stresses, the command is block face apply. When we're applying velocities, the command is block grid point apply. When you're applying a stress, of course, stress is force over area. So there needs to be some area associated with the region over which you are applying that stress. So you can't just apply a stress to a grid point. You can only apply a stress to a face. You can fix the grid point so it doesn't move. You can't apply stress to a grid point. You can apply force to a grid point, but you don't want to use your calculator to work out what the force should be on every grid point to give you the right stress. Instead, you say block face apply stress, and it works out the forces for you based on the area of the faces. We solve that. Again, it should solve in a couple of steps. We delete the tunnel exactly the same way we did before. We solve again, and we save it. So we can run this whole thing. Right, this took a little bit more steps to solve. We're at about 2,000 here. Let's go look at the plot. So if we go to the block plot, here's the displacements. Look at, this is interesting, how we have non-blue colors up at the top and the bottom here. And even in these corners. Remember with the displacement boundary conditions, obviously the displacements at the edges were 0. With stress boundary conditions, this is clearly not the case. We have non-zero displacements at the edges. We can actually quickly compare to the previous state by just double clicking on it here. So under save states, I can go here and double click on bound fix.save, and it will restore the other state here. You can see that there's a fairly noticeable difference. And even the maximum displacement here, 0.2 in the case of displacement boundary conditions, and 0.26 in the case of the stress boundary conditions. I'll just go sideways here and show you another useful plotting trick. For numbers like this, you don't necessarily need it in scientific notation. What you can do is change the number format here. So if you go over to plot item list, click on block displacement magnitude, go to legend, the contour. Under here it says format scientific. That's the default. You know, for numbers like this, I don't need to see scientific notation. I can just change it to decimal, and it's going to give me the decimal version of the displacements here. This will be a disaster if we go and look at stress. So let's change it back to scientific, because now we're going to plot stress. So scroll back up here, change the contour to stress. It remembers that we were plotting the minimum principal. It remembers that we want compression positive. It remembers that we're doing this volumetric averaging to give us a smoother state. So here's the stress state for the stress boundary conditions. So the maximum compression here is 2.7 MPa. With the displacement boundary conditions, the maximum stress was about 2.3 MPa. And if you really want to dig into the details, you can look at the histories here. So here's displacement history for the fixed boundary conditions. Here's displacement history for the stress boundary conditions. Again, you can see more displacement. Here's stress. And you see less stress in this case. So this is kind of an extreme example. All the material is elastic. The boundaries are quite close to the tunnel. But really, this is just to demonstrate the effect of the boundary conditions and how to go about applying the boundary conditions. And also the initial conditions. And that is the end of this tutorial. There are more to follow.